So hi and welcome everybody. So in this talk we were going to give an overview of the basic building blocks for the scalability of Elasticsearch. That's this fancy title. So before beginning, I would like to introduce a little bit myself. My name is Iraklis, not Elias, just to make sure, right? So I'm a principal software engineer at Elastic, and previously I was at Oracle Labs in Zurich, focusing on scaling up graph analytics and financial applications. Before that, I did my PhD at EPFL on scaling up analytics, and I got my degree here at Entua in Athens. So the agenda for the talk is this. So we're going to talk a little bit about what is Elastic, right, who we are, and Elasticsearch, one of our technologies that will be the main focus of this presentation. And then we're going to begin to see how Elasticsearch scales out with shards to multiple machines, how we can do distributed aggregations and searches in that setting, a little bit on shard recovery, what is cluster state and why is it important for distributed systems like ours, and then a little bit more advanced topics on scaling data, time series data with data streams, and another component that we have called ILM, Index Lifecycle Management. And we're going to conclude with our future of the serverless vision that we have for unparalleled scalability. Right, so just a forewarning that this talk may contain some personal views, hopefully nothing erroneous, but it's not officially endorsed. So let's begin with Elastic. So Elastic helps the world's leading organizations accelerate results that matter by putting data to work with the power of search. What does that mean? Basically, we're not just storing the data, we give the tools to organizations to gain insights out of them. That's why we say we put them to work. And it's a publicly traded company. Our technologies have or are used by a lot of organizations out there, so these are just some examples. I'm pretty sure that you can recognize many organizations such as Tinder or Uber or other technologies. But they span from the technology sector to the finance sector and the healthcare and basically all the sectors out there. What Elastic gives to organizations is the Elasticsearch platform. Basically, this comprises of three main solutions that you see at the top. So we have the enterprise search, right? This is for search and analytics at a scalable level on massive data sets. We have the observability solution, which is for the correlation of logs, metrics, and application traces, right, to reduce the mean time to response. And we have the security solution, which is used to basically real-time protect your infrastructure. And these solutions use this technology stack that we have, which is comprised of three main technologies. We have the Kibana, which is used for exploration, visualization, and engagement. We have the Elasticsearch that we will focus on in this presentation, which is for storing, searching, and analyzing. And we have a lot of integration tech out there for collecting data and alerts. All these solutions can be run either on public clouds, such as Amazon AWS, Microsoft Azure, or GCP from Google, on hybrid infrastructure, or on-premise, right, on your infrastructure. So let's go on directly into Elasticsearch. What is Elasticsearch, for those that don't know it? It's a very popular, distributed, scalable, highly efficient, and resilient search and analytics engine. It's free and open, so you can find it on GitHub, actually, and check the code and contribute if you would like. And if you go to DB Engines, which ranks the most popular databases out there, it's actually the 8th most popular database out there. And databases usually have some strong specialization. So here you can see that it's actually the first search engine database out there, right? So we're the most popular one on that specific field. Now, our power is based, and you will see that we use a lot, Apache Lucene. I'm going to explain to you in a little bit what that is, but it's basically a very popular open source project that we use that helps us do search. But it's important to understand that it's not only simple searching that we enable, things like grepping or some sort of simple regexp that you can find in SQL-like. We do stuff like ranked results, right? So you get a score with the results. We can do fuzzy matching, so you don't need to have exactly the word that you search, but some variations of it. Complex search expressions, we do things like spell corrections, synonyms, phrasings, stemming, and other stuff. And we have extensions and more advanced features such as time series, geospatial, machine learning, and vector search. Okay, so this is enough a little bit about the high-level stuff and what are these. So let's go directly into how the technology is built up from the bottom up to the scalability notions that we use. So we will start at the bottom where you can find what we call an inverted index. So this is a basic data structure in computer science which helps us figure out which documents in your document database contain searched terms that clients wants to search for. So let's do that with an example. So here you can see a database, let's call it, that has two documents, the ones that contain these sentences that you see up there. Right, so in order to search for terms, what we do is build an inverted index, which looks a little bit like this. So basically, it's a map from sorted tokens. So you get the tokens out of these documents, you put them in a sorted order, and this enables you to search for them efficiently. And then for each term, you correlate it to which documents contain that term. So as an example, you can see for that brown word is contained both in documents 1 and 2, while, for example, jumped only on document 1. So let's assume now that users want to search for lazy and dog. So you would go into your inverted index. You would see that dog is contained on document 1, lazy in both documents. So you would return, because you want lazy and dog, only document 1. You could, of course, have searched also for lazy or dog. In this case, you would return both documents, right? But it's important to understand that you get also scores out of this technology. I'm not going to spend time explaining how the scores get created, but you might imagine, for example, that because document 1 contains both of these words, it might have a higher score than document 2. Right, and this is the basic of what Apache Lucene is, the open source project that I mentioned, what a Lucene segment is. And right, so let's spend a little bit more time to understand what a Lucene segment is. A Lucene index is comprised of multiple segments. Segments in Lucene are immutable. That's like a basic property of them. And each segment is a self-contained, self-efficient inverted index. Now, this immutability gives us some advantages and disadvantages. The main advantage is that they are read efficient, so you can pretty quickly search them, and it uses a lot the file system cache. But there are some disadvantages. We need to do a lot of housekeeping, and Lucene also needs to do a lot of housekeeping. For example, in order to support deletes or updates, updates are always written on the last segment of an index that is in memory. This is visualized here like imagine that you just added the token there because you added it in one of the documents, for example, right? But the index, you can imagine it as a chain of these immutable segments that are on disk, and the last one that is in memory. And some more advanced housekeeping that we need to do, things like merging them from time to time and stuff like that. But the basic data structure looks like this. Apart from the inverted index, there are other stuff that we store there, stuff like metadata like term frequencies in order to support relevancy queries, positions, offsets, and stored fields like the actual documents themselves. Now, we talked about Lucene, which is the basis of our text search capabilities. Let's go in to see what Elasticsearch does on top of Lucene, what additional steps it gives you in terms of scalability, which is the main aspect of this talk, right? So the basic notion of how Elasticsearch scales out is with the notion of shards. Basically, a shard is a Lucene instance, a Lucene index of what you just saw before, this chain of segments, right? And we distinguish shards in two types. In Elasticsearch, we have the primary shard. What does that mean is that you can basically, for your high-level notion of an index of similar documents like books, for example, that you want to search, you can split your data across multiple Lucene instances, and each of these ones, we call them a primary shard. So this gives you the capability to scale ingestion. So imagine if one Lucene instance has some limit on how much fast you can ingest data, you can simply have another primary shard to ingest more data into your Elasticsearch index. And then we have what we call replica shards, which are basically automatically synced copies of their primary shards. And these are read-only, right? Because Elasticsearch automatically syncs them as you do ingestion at the primary shards. And these are used for query scalability, right? So for your queries, imagine that again, if you have one Lucene instance and you have some limit on how fast queries can be served, then we have also more replica shards to support more queries. Here is some visualization to help you out understand this organization of notions. So imagine that you have an index in Elasticsearch called children books, and this is like one primary shard that we have here called P0, and this has this Lucene instance that I visualized before. It contains other stuff, of course, right? But I'm trying to simplify it for this presentation. And this is the example that we saw before. You can have another primary shard for the same index that might have more documents and more terms inside it, right? So when we do search queries, we go to both of these parts of the dataset of the index. And then you can, for example, say that I want to have 2 replica shards per primary shard. So you would have 2 more replica shards for each primary shard, which I denote with the keyword R0, replica 0, and replica 1 for primary shard 1. Right, so apart from scaling ingestion and queries, one other good thing that Shards provide us is that you can very easily scale out to multiple machines simply by placing different shards on different machines. So Elasticsearch does that in a balanced manner, so we have some cleverness in how we distribute the shards around so that we can also balance the workloads. But let's go through one example to see how that works. So imagine that you have one node in your machine cluster, right? And you have an index called logs with just one primary shard, P0, that sits on, of course, on node 1. Imagine that you have now another index called products with 2 primary shards, P0 and P1. They're still on node 1 because that's the only machine that you have. And let's say that you add another node 2 to your cluster. So Elasticsearch will automatically balance the data and will move one of the primary shards to node 1. So in this case, P1 to node 2. Imagine further that you now say that you want to have one replica for the logs index. Elasticsearch will automatically put it on node 2. Right, so that is useful for fault tolerance. So we try not to collocate the replica shards with their primaries. Why? Because if one of the machines fails, then there is another replica or primary on some other machine. And a little bit more complicated example where we have now one more replica for the logs index and one more replica for the products index. So you can see here that it tries to balance things out. So it would put another R0 on node 3 and another, and it would spread the replicas, the new replicas for the products index across the 2 machines. So if any one of those machines now dies, we still have our data intact because of this balance. Right. So let's go forward to understand now how distributed searches are done in such a setting. So imagine now that, and we'll see that with a visualized example. Imagine that we have now these 3 nodes. We have the products index that I just showed you with one primary on node 1 for the first part of the data. The second primary is on P1, which is stored on node 2. Right, and we have the replicas that is, each is the replica of their primaries, R0 on node 2 and R1 on node 3. Any one of these nodes can receive a query. This becomes like the coordinating node for this query. So let's imagine in this case that node 2 receives a query that says, I want you to get me the top 5 products whose description has the term denim inside them. Right, what Node 2 will need to do is that we will need to send this query to both parts of the data because we have split the index into two parts, right? So it will send the query to either the primary shard or one of the replica shards for each part, for each of these two parts of the data set. Right, in this example, let's assume that it picks to send the query to P0 for the first part, so the first primary, and to R1, so the replica for the second part of the index. Each one of these two nodes will do the top 5 query inside it, and it will send back the results to node 2. Node 2 will combine these results, so we will have like 10 results, and it gets also the scores of these results, so it can sort them out and figure out the real top 5 results to return to the user. It can also optionally go back to the servers to fetch any additional, oh yeah, I skipped one, so this is the sorting phase, and then it can optionally go and fetch maybe the full documents from the nodes to, if the user requested them, to return them back to the users. And it returns the result to the client. Aggregations are a similar, are executed similarly. Just to clarify what aggregations are just another type of analytics with which you can slice, dice, and combine data to get insights. And here we will see one example. They're broadly executed in a similar manner, except for some sort of more advanced analytics, which I will not focus on, which might need to centralize or estimate data. But let's see another example. So imagine that you have your 3 nodes again of products, and node 2 now receives a query to do an aggregation that wants to sum up, right, to add up all the prices of all the products in the index. So again, it will need to choose where to send the query to either a primary or a replica of each of the 2 parts of the index. Let's say in this case it chooses to send it to R0 for the first part, which is on itself, and then to R1, replica 1 on node 3. Each of the 2 nodes again will do the local sum. They will send back the result to node 2, which will add it up and send it back to the client. And this is how aggregations work. Right. Now on to shard recovery to explain you now how when one of the node fails, what happens to the shards and with fault tolerance. So we distinguish what we do based on the type of the shard. If a node dies and it had the primary shard, what we will do is that we will choose one of the other replica shards on the cluster and promote it to become the primary shard for that index. And if one of the replica shards is lost, then simply we copy a new replica out of the primary onto a new node. So let's do that with a visualized example. So let's say that we have again these 3 nodes with the products index that we saw also before, and node 3 dies out. So replica 1 is lost, right? So what Elasticsearch will automatically do is that it will copy a new replica out of the primary shard P1 onto node 1. And again, now with this balance of shards, even if one of these 2 servers again dies, we still have intact the whole data. We don't lose it. Right, now you might wonder how Elasticsearch knows about the machines, about where shards are, and how it does all this fancy and clever stuff. Right, for that we have a very important data structure that we call the cluster state, which simply is a metadata data structure that contains the most important stuff about the cluster. Things like the cluster membership, like which nodes are part of the cluster, and data placement, where the shards are allocated, on which nodes and what type they are. We have one elected master in the cluster, which is responsible for proposing updates to this cluster state and propagating to the rest of the servers of the cluster so that they have a complete and up-to-date information of the rest of the cluster. It processes these updates based on events such as when a node joins or leaves the cluster, or you create another index or shard. It is also responsible for doing some health monitoring and can detect if a node has left the cluster or a new node requests to join a cluster. It's important to understand that these updates to the cluster state and the cluster state itself is not in the critical path of ingestions and read queries. Why we need that is because distributed systems are quite complex systems, right? You can have many weird situations where nodes are operating at different speeds. They might be leaving or joining the cluster. It's a bit chaotic sometimes, right? So we need some sort of consistent view of the most important information of the cluster. And that's what the cluster state gives us. And in order to update it, we use a consensus protocol in order to establish that the cluster state is updated according to a majority of a subset of machines that we call the master eligible nodes in the cluster. And when the majority of them votes yes on a specific update that master proposes, then it's established. We say that the quorum is achieved, and we have the cluster state propagated to correctly and established across all the servers of the cluster. These master eligible nodes also serve another important aspect, that if the master dies itself, they're also responsible for electing another master in order to continue and move forward the cluster state updates in the whole cluster, actually. Let's see how that works in practice. Let's assume that you have now a brand new cluster that you start with Elasticsearch, which has these 3 nodes, and these 3 nodes are the master eligible nodes of the cluster. We don't have a master yet, so we will talk about how the cluster is bootstrapped. That's how we call it. So randomly, one of the nodes, let's say node 1 in this example, will propose to become the master of the cluster. It will propose that to the other 2 servers, and these 2 servers will need to vote on this proposal. So they will vote yes to node 1. Node 1 will receive these votes. It will see that it has a majority of the votes, and will then deem itself to be the master of the cluster. It will also commit this new cluster state that it just created. This CS1 that I denote here means cluster state version 1, basically, which as a metadata says that there are 3 servers on the cluster, and node 1 is the master. So as soon as it sees that it has a majority of the votes, it will then also commit this new cluster state to the rest of the nodes, which will acknowledge back to the master, and we say that this cluster state version 1 has been established across the cluster. This is the basic premise of this cluster state updates, and this is just one event that I showed you, like bootstrapping, but basically whenever you have nodes joining or leaving or index created, the basic premise is followed. So let's see that with another example. Let's say that you have a node that joins, node 4 in this example, it requests to join the cluster. So what master will do, it will create another version of the cluster state version 2, which contains node 4 as another member of the cluster. It will propagate it to the rest of the servers, who will again acknowledge back to the master, and this acknowledgement also includes the yes votes for the master eligible nodes. Master will see that it has again the majority of the votes, so it will commit the new cluster state to the servers, who will acknowledge back, and now we say that we have a cluster state version 2 established across the cluster. Just a very quick visualization on that. The same thing happens when you create a new index. Master decides where to place it. In this example, I'm not showing you the whole flow. It decides to place it on node 4, for example, and it creates a new cluster state version 3 in the same way that says, okay, primary shard 0 of that index is placed on node 4. Now that we saw how this works with a cluster state, let's go on to a bit more advanced topics on how we scale even more data with Elasticsearch, and we will focus on specifically how we deal with time series data. This is a very important class of data because a lot of use cases use time series data, meaning that basically you have a stream of data and you usually append only data, you add new data, and the older data age with time. This is, for example, what happens with logs usually. So a lot of people are using Elasticsearch for logs, so this is a very important use case. And imagine that as you have new logs from your applications, you put them to these Elasticsearch indices, and the data becomes older and older. In order to scale this type of data, there is a notion that we call data stream. And basically, this is a logical organization of a series of indices that contain your data. Imagine, for example, in this example that I visualize here, that you have an index per day of ingested logs. So here you have like an example of 3 days. The most recent index in the data stream is the one that receives the updates, while the others do not receive updates, and they have the older data. This is also, okay, the arrows were the mistake there, but it's the next animation. This is also very useful for searches, because searches usually tend to target the most recent data. So imagine that now that you do a query that targets like just 2 days and yesterday's logs. So we know that this query needs to be sent only to the 2 last indices of this data stream and not to the older indices of this data stream. Apart from that, now you might notice that this older data usually receive less traffic, right? Receive less search queries. So we have another notion that we call the index lifecycle management here, that exploits this characteristic in order to give you a trade-off of cost and performance for this older data that receive less traffic. Basically, as the data get older, we put them on data tiers, that's what we call machines that host this older data, on different data tiers that are gradually cheaper and maybe slower. So let's see how that works. Here I have extended a little bit the data stream, as you see, so we have more days of logs. Again, the last one, the most recent one, is the one that receives the updates. And below them, I have denoted the tier that these indices will be stored on, basically the machine types and the kind of settings that we will use for these indexes. These data tiers have names, and they're hot, warm, cold, and frozen. What does that mean? Like the latest one, the most important one, the one that receives the ingestion and has the recent data and receives most of the queries, is stored on the hot tier. These are, we have settings like a high number of replicas, like 2 replicas per shard, so that you have high fault tolerance. And we might have beefier or more expensive machines in order to have faster queries and ingestion for them. You might have, for example, also SSD disks for this, which are faster than magnetic disks. As the data gets older, you might elect for the warm tier, which has, for example, cheaper and slower machines, for example. Like you might elect for having only 1 replica for your shard, so a bit decreased fault tolerance, but you might also use smaller machines or magnetic disks in this case. Now, for data that gets so much old that is basically read-only and doesn't receive any ingestion, we have the cold tier. Basically, what happens here is that we don't have any replicas at all, we use a cloud object storage like Amazon S3 or on Azure or GCP equally an object store to store a snapshot of your cold data for fault tolerance. So if a machine dies, we can fetch it from the object store. This is for read-only data, and on the cold tier, we fully cache that data also on disk, on the cold nodes, in order to service queries. And for even older data, we have the frozen tier, which is basically these searchable snapshots that I just mentioned. That's how we call them on the object store. But we have partially cache them on the local disk of the machines. So as queries come in, we dynamically fetch data from the object store. We put it on disk in order to serve the search queries, and this is how the frozen tier works. And this is even cheaper. Now, after explaining you all these notions about scalability, I want to conclude with how we envision the future with serverless in order to achieve unparalleled scalability. So the basic premise that we want to use is stateless, meaning that we want to move the state from the machines onto a cloud object store like S3 or on one of the other cloud providers. So we want to move stuff like indices or the cluster state there, both for fault tolerance, but mostly for fault tolerance. And we envision also to have like just 2 data tiers, so not all these data tiers that I just told you, but just 2, the search and the ingest data tier. The ingest data tier that you can see on the left side of the bottom layer of our new vision is composed of the servers that will, of the machines and nodes that will receive your ingestion, while the right-hand side, the search tier, we have the machines that will service the queries. And how we will synchronize basically the data between the 2 is through the object store, the cloud object store. We can achieve up to 75% performance improvement for ingestion, just because we will not have any replicas at all in this new infrastructure. Why? Because the data is actually also on the object store, so we do not need them for fault tolerance. And the basic advantage that these 2 data tiers will give us is that you will be able to scale each of these data tiers independently. So you can scale up the ingest tier for more ingestion, and you can scale up separately the search tier for more search power. Right, so as a summary, what we saw in this presentation is how Elasticsearch achieves unparalleled scalability as a search and analytics engine. We talked about how we usually seen at the bottom layer and how Elasticsearch scales out with the notion of shards. We saw how distributed searches and aggregations work over multiple nodes. How the master nodes is responsible for directing cluster state updates across the machines of the cluster. We saw how we scale time-based data streams with index lifecycle management, and the future of our serverless vision for even more scalability. For the interested readers, I also mentioned some examples of scalability out there, both from external and internal use cases, and a lot of blog posts, which I can share with you the exact links for anybody who's interested, that you can see more details on scalability notions. Right, and just before closing, I want to mention that we also have a very vibrant community that you can be part of. So feel free to check out all these links. We have discussion forums, we have community videos, we have newsletters that you can also learn about hot stuff and how we deal with AI, for example. We have a contributor program that you can earn swag and stuff if you contribute. We have a careers website, of course, so if you're interested. We have a very good remote first culture. We have over 2,600 employees across 40+ countries. And of course, subscribe to our meetup if you're based here, Greece Elastic meetup events. And the next one is expected to happen in June. Right, thank you very much, and hopefully